Hi everyone and welcome to another PAT Problems video. My name is Helena, I'm the Access and Outreach Manager for the Department of Materials at the University of Oxford, and today I'm going to be taking a look at question number 19 from the 2015 PAT paper. So as with the other videos in this series this summer, we are focusing on questions which could translate themselves into the new multiple choice format for this year's PAT paper. So let's have a look at this particular question. So here we are being asked to consider a circular orbit of radius lowercase r around the Earth. If the Earth's mass is big M and the radius is big R, and Newton's gravitational constant is big G, derive an expression for the speed that is required for a stable orbit. Okay, so let's start with this part of the question. The first thing I want to do is draw a picture. So here we have our Earth, mass big M and radius big R, and we have our object in a circular orbit, which has an orbital radius of lowercase r there. So let's say that this is a satellite with mass lowercase m there. We want to find the speed required for this to be a stable orbit. Right, so let's think about the forces that are acting on our satellite orbiting the Earth. We have the centripetal force, the force due to the circular motion, which is mv squared over r. And we also have the gravitational force between the two objects with the certain masses, which is g mm over r squared. So for this to be a stable orbit, we can equate the two. Luckily, we can divide through it by the mass of the satellite because we don't know that. We can also cancel out some of the radiuses there, which gives us an expression for v squared, which is g m over r. Or if we square root that, the expression for the speed, which is the square root of gm over r. So that is our expression for the speed for a stable orbit, as described in the question. Okay, second part of the question. Assuming that the radius of the Earth is 6,400 kilometers, so our big R is 6,400 kilometers, which is equal to 6,400 times 10 to the 3 meters. I'm going to write that in SI units there so I don't make any mistakes later. And the gravitational acceleration, G at the surface of the Earth is 10 meters per second squared. So G is 10 meters per second squared. Calculate this speed required for a stable orbit around the equator at sea level. So in this case, the radius of the orbit would be the radius of the Earth here. So our lowercase r in this expression is going to be big R, which is the radius of the Earth. So in this case, our v is a square root of gm over big R here. Now, we're not told what g and m are, but we can figure out a way to equate that to something that we do know. So let's think about the forces that are acting on someone or an object which is at the surface of the Earth at the equator. So if we have an object of mass m, we have its weight acting towards the center of the Earth would be mg. And this is also equal to the force due to the gravitational force between those two bodies, which is g m over r squared. So our radius of the Earth is our distance there. Again, we can cancel our masses, which gives us an expression relating g, which we do know, to some constants that we don't know. So let's just rearrange this to get an expression for gm here, and then we can substitute it into this expression for v. So we would have that r squared g is equal to gm. Substitute that into here. We have that v is equal to r squared g over r, which, if we simplify that, is equal to the square root of r times g. Let's put some numbers in now. So if we put our numbers in, we have that v is equal to the square root of 6,400 times 10 to the 3 times 10, which, if we either do that on paper, in our heads, or in a calculator, gives us a value of 8,000 meters per second. So that's the value of the speed for our stable orbit around the equator here. Now let's go back to the final part of the question, which is asking what physical reasons would make it difficult for a satellite to maintain this type of circular orbit around the equator at sea level, even if one can ignore the atmosphere? Well, let's just physically think about the shape of the Earth, right? It's not a perfect sphere. So if we're trying to maintain sea level around the equator, we would have to go through some land masses, some mountains, for example. So in reality, if a satellite is trying to stay at sea level and move around the equator, it's going to pretty quickly smack into something and smash. So physically, that's not possible. However, we've theoretically calculated the speed that it would need to be traveling at in order to do that there. Okay, so that's one way to answer this question. If this was in the new format of the PAT paper, there would just be a few options for you to select from, given the multiple choice format, but the content of the question could be quite similar. So I hope that was useful. Thank you for watching, and please join us again for another PAT Problems video.